All right, folks, we're going to introduce section 5.3, the section known as volumes by cylindrical shells, specifically rotational volumes. We're going to introduce and motivate this section by actually looking at an example. So let's take a look at the following. We're going to find the volume of the solid obtained by rotating the region bound by the curves y equals 2x squared minus x cubed and y equals 0 about the y-axis. So let's take a look at that region and talk about it. So let's see, forgive the crudeness of my graph, but it looks something, looks something like that. That is y equals 2x squared minus x cubed. The reason I know it looks like that is because if I factor out an x squared, I get x squared times 2 minus x, which means that it passes through the origin at 0, 0 and behaves quadratic there. It also passes through 2, 0, this other ordered pair. And I know that it's oriented with the right side down and the left side up because it has a negative leading coefficient. So it's just a little bit of pre-calculus review for graphing some polynomials. The other curve is the line y equals 0. Let's do a different color there. That's this bottom line here. I'll do in red. Y equals 0, and then we're going to rotate that about the y-axis. So this is the region bound by those curves. And it's going to generate a shape, I guess we're going to call the dog bowl again here. Let's see if we can draw this one a little bit better. Something like that. That one looks more like a dog bowl than the other example that we had done where I called it the dog bowl. But this is our axis of rotation. Right, and this was the region that we were talking about right here. So anyway, we're going to talk about the difficulties of setting this up using the previous technique, the technique of discs or washers. So if we talk about the technique of washers in this case, since we're rotating about the y-axis, we should do some horizontal cuts. So let's see, there's our approximating strip. That's going to translate into the following shape. Right? We're going to get this disc with the hole in the middle, which we're calling a washer. And so this is going to be with a thickness dy washers. So we might think then that the volume is the integral from y equals, I guess y equals 0 here, the bottom, up to some as yet unknown ordered pair, y equals, I don't know. So there's maybe problem number 1. But let's get our form in here. We're going to use washers pi capital R squared minus little r squared for washers dy. So problem number 1. And these aren't insurmountable problems, but they're problems for us nonetheless. Problem number 1, what is the max height y value for the upper limit? Now that's not necessarily hard to figure out, but you would have to use Calc 1, and what would you do? Well, you'd find the local maximum. You'd take in this curve and you'd say, all right, well, the derivative is 0 there. That shouldn't be too hard to figure out. And you can find the x value, and that is going to make that happen. And then the corresponding y value. Okay, but that's problem number 1. Problem number 2 is this. Because we're using washers, we're going to have an outer and an inner radius. So here's our outer radius. From the axis of rotation over to the outer curve, that's our capital R. And the inner radius is from the axis of rotation to the inner curve. Whoops, come on. Inner curve, little r. However, in this particular case, capital R and little r are defined by the same curve. So, what's going on here? So, problem number 2. capital R and little r are defined by the same curve, which means that capital R squared minus little r squared is going to be 0 unless we take the curve y equals 2x squared minus x cubed and solve for x as a function of y. Now, I don't know when the last time you completed the square was or how good you are at that. But I'm willing to bet that nobody in this class knows how to complete the cube. So x equals, I don't know. So that's going to be real tough for us to do. I mean, seemingly if we could do that, we might be able to break this up into the right side and the left side of the curve, just like we do with a plus or minus of a square root. But really, that's trouble. So instead of addressing these concerns directly, we're going to bypass them using a different kind of geometry and a different technique. Instead of building up the volume of a solid in much the way that you would build a wedding cake, right? One disc or washer on top, and then another disc or washer underneath that, and so on and so forth until you build this thing up bigger and bigger and bigger, and you get this rough approximation of your volume. And maybe in this case, I'm roughly approximating an egg or a sphere, right? So there we're using layers of discs or washers to approximate the volume. Now that technique was section 5.2. What we're going to do is, let's say we have that same spherical volume we're trying to approximate. Instead of using layers or slabs, we're going to use core samples. So I'm still going to use a cylinder, but I'm going to use, a tall skinny one here for the center, and then wrapped around that is going to be another tall, skinny cylinder. And then wrapped around that is going to be another tall, skinny cylinder. And then maybe one more around the outside there. Now, this is getting a little bit messy. But think of it as like nested tubes, right? So if maybe I should shade some of these in. There we go. It's maybe a little bit easier to see that way. So instead, we use nested, what we're calling shells, or sometimes what I refer to as cores. So, when you got your PhD and you're studying the ice down in Antarctica, you take an auger, like a drill, and you drill down into the ice, and you pull up this tube of ice. And then once you pull that out, think about your first drill bit size, your first auger size as you drill into the ice and you pull that up. Then what you're going to do is you're going to drill back in the same hole, but you're going to get a bigger auger this time, right? And that's going to take a bigger core sample, but it's already missing that original core. And then you're going to do it again. You're going to get a larger auger, and that's going to make an even bigger core sample, but it's missing not only the very first core sample, it's also missing the second core sample. And so you have this series of nested shells coming out of this thing. So let's take a look at the geometry of one of these shells. This is the shell geometry. Now what we're going to do is we're going to take one of these shells, toilet paper rolls, I guess. If you were going to do some kind of elaborate construction out of different sized toilet paper rolls, that's what we'd be doing here. And we're going to take some scissors. Drawing my scissors there. And we're going to cut this sucker right down the side. Snip, snip, snip. And then what we're going to do is we're going to take this shell and we're going to roll it out flat. So I'm going to cut there and then I'm going to open it up a little bit. All right. Shell starts to look something like this. All right. And then eventually, it's not exactly a rectangular solid. It's going to have a little bit of a bevel to those edges because that inner radius is a little bit smaller than that outer radius. But we're going to neglect that difference because in the limit as n goes to infinity, the number of our core samples is going to get larger and the thickness of that shell wall is going to get thinner and thinner and thinner. And now what we have is the volume of a rectangular solid. So the volume here is the length times the width times the height. So let's see. If you have a certain function, typically speaking, this height is usually defined by your function of x. The thickness here depends upon what variable you're cutting with respect to. Now, if this is on the xy axis, the thickness right here of this shell wall is actually a small measure on the x-axis. So the thickness is delta x, or dx in this case. And then the tricky part might be the length. But this length here is this distance around the top of the shell, which is its circumference. So the circumference is then 2 pi times whatever the radius is, r. So generically speaking, the volume of a single shell is something like VI equal to 2 pi times its radius times its height. dx in this case. It could be dy depending upon how we rotate. And the volume total is going to be the sum of all the shells from A to B, which is 2 pi r h dx, or alternately c to d 2 pi r h dy. Now, in either one of these cases, here r and h are functions of y, and here r and h are functions of x. So let's take a look at our dog bowl back up here and try this again. I'm going to redraw the region. Try to draw this function again a little bit better. X-axis, y-axis. This is the curve y equals 2x squared minus x cubed. We're talking about rotating this region here about the y-axis. And now, when I draw my approximating shell here, my shell is wrapped around the axis like this. And I always tell students that they should draw that little approximating shape here. Because in this instance, and this is an important concept, the thickness is the thickness of the shell wall, and that's dx, which is quite a bit different than, say, using a disc or a washer, which has a thickness dy. So right off we should note shells versus disc or washer. They use opposite differentials. If this is dx, then this is dy, and if this is dy, then this is dx. So they are not using the same variable. They're actually opposite variables. Now, this shell wall here is now part of this vertical strip, and that would get wrapped around the axis like so, and it would create our shell. So let's talk about what our dimensions are. In this particular case, the height of the shell is the function f of x, which is 2x squared minus x cubed. The radius of the cylinder is measured from the axis of rotation, this time out to the shell wall. Now, this is where it gets confusing for some students. That radius r is not from the axis of rotation over to the left side of the curve, over to the right side of the curve. So the curve actually has nothing to do with it. What's going on is we're using a series of vertical approximators, and they each have their own radius at different locations. And those radii range from x equals 0 all the way out to as much as x equals 2. In fact, it's a general distance measured from the y-axis over. And remember that the general distance from the y-axis over to a spot is x. And so in this particular case, the radius is just x. And so our volume is the integral from x equals 0 to x equals 2 of 2 pi times the radius, which is measured by x, times the height, which is the height of the shell, which in this particular case is given by the function 2x squared minus x cubed integrated dx. And this is going to be 0 to 2, 2 pi, 2x cubed minus x to the fourth dx, which is 2 pi times, let's see, 1/2 x to the fourth minus 1/5 x to the fifth, from 0 to 2, which is 2 pi. When we plug in 2, we're going to get 8 minus 32 over 5 minus the 0 when we plug in 0. And this is 2 pi. 8 is 40 over 5. That's not an 18, that's an 8. 40 over 5 minus 32 over 5 is 8/5. And this turns out to be 16 pi over 5 for the volume. So, a couple of things I want to say about the shell method. Obviously here, the key is that it's going to be using an opposite differential than you're used to when you do discs and washers. So when you set up your axis of rotation, draw either a disc, washer, or shell, and then note, is my thickness part of the x-axis or is my thickness part of the y-axis? And that will tell you which variable to use. The other thing is, if I give you a problem, some of these problems can be set up two different ways. So you don't always have to use shells and washers, but as we saw in this problem, it was quite a bit easier to use shells in terms of the setup than it was to deal with these different problems, 1 and 2, that we had with using discs and washers. So there might be a preferred setup. Thirdly, if I give you a problem that can be set up both ways, you really need to understand that if you're going to set it up with discs, washers, versus shells, they're going to have those opposite variables. So keep that in mind, and we'll take a look at some examples in the next video.